I'm Jingyi and I'm a PhD student at University of Cambridge. I'll be presenting our paper on the benefits of sensorimotor regularities as design constraints for superpower interactions in mixed reality on behalf of my co-author, Kristensson. Superpower interaction is about enabling users to do things that seem impossible in the real world. Mixed reality enables these novel experiences that feel real yet transcend human capabilities and what the physical world can offer. But designing these interactions comes with challenges. With no real-world equivalents to draw on, it is difficult for designers to decide which action would intuitively lead to a certain superpower outcome. The mismatches between designers' choices and user expectations can make this superpower interaction difficult to learn. And then there's perceived ownership. How much users feel that the superpower is truly theirs. If an interaction does not match their expectations, it can break the sense of presence, making them feel like they're not in control. Some researchers have explored drawing inspiration from superhero narratives, which may not be universally understood. Possibly due to a lack of effective design methods, many superpower applications in MR have defaulted to using conventional input techniques like controllers and buttons to produce different superpower outcomes, which may not fully utilize the capability of modern MR headsets. There is still no clear best way to design superpower interactions that are both easy to learn and feel intuitive to general users. One promising candidate for such design constraints is the concept of sensorimotor regularities, which we define as image schemas and how they relate to each other. Since early infancy, humans develop a set of abstract cognitive patterns, in other words, image schemas, from repeated sensorimotor experiences. For example, we learn the image schema slow by actively moving or observing the movements of others. And we learn the image schema resistance by encountering a resisting force when we forcefully interact with objects or people. Such a resisting force tends to cause our movements to slow down. Repeated experiences like this lead us to learn the entailment between resistance and slow. These universal entailments between image schemas allow us to intuitively predict outcomes based on actions taken and decide actions to take based on the desired outcome. And this could be also true even under novel dynamics like using a superpower in MR. We hypothesized that creating action-outcome mappings of superpower interactions based on these universal sensorimotor regularities could lead to better user performance, more efficient user learning, and a stronger sense of agency as well as presence. To investigate the hypothesized benefits of sensorimotor regularities, we chose an augmented superpower, the ability to control the pace of time, to be the investigation context. Specifically, users can perform one action to slow down time and perform another action to reset the pace of time. We designed 3 different methods to control the time manipulation superpower. The mid-air button method, a method that does not follow sensorimotor regularities, and a method that align with sensorimotor regularities. Since many previous superpower interactions in MR rely on well-established input techniques, we used the well-established MRTK3 mid-air button as a calibration point to investigate potential benefits of sensorimotor regularities congruent mappings, as well as the potential risks of sensorimotor regularities incongruent mappings. We kept its default visual and audio settings, but scaled the button to roughly match the dimensions of an adult's palm and positioned this button within easy reach of the user's left arm to improve usability. To design sensorimotor regularities congruent mappings for the time control superpower, we followed 3 simple steps using the ISCAT image schema database. First, we identified slow as the key schema for slow down time and fast for reset time speed. Then we found that the schema that will most likely lead to the outcome of slow is resistance, and the schema that will most possibly lead to the outcome of fast is restraint removal. Finally, the schema resistance can be effectively represented by the commonly used gesture of grabbing. and the schema restraint removal can be well represented by another commonly used gesture of releasing. With this method, users slow down time with a grabbing gesture and resets with a releasing gesture. To explore the effects of arbitrary mappings, we intentionally violated sensorimotor regularities by assigning right as the cause of slow and left to be the cause of fast. While we all know that the image schema right is unlikely to yield the outcome of slow, and similarly, left is unlikely to produce the outcome of fast. With the sensorimotor regularities incongruent mappings, users slow down time by swiping their thumb towards right and reset by swiping towards left. To encourage participants to use the time control superpower, we developed 3 MR games on HoloLens 2 where players had to catch rapidly falling visual objects. It is something nearly impossible without slowing down and resetting time. In all 3 games, players used their left hand for time control and their right hand for game tasks. We conducted a within-subject study with 18 participants, testing 3 superpower control methods across 3 games. The study started with a familiarization phase where participants received an introduction to the game tasks, rules, and interactions. Then, in the test phase, each participant played 32 trials of each game, using different actions for time manipulation. After each game, they completed a set of questionnaires. The results show that the sensorimotor regularities congruent method enabled significantly higher success rate compared to both mid-air button and the sensorimotor regularities incongruent method, and it also enabled significantly shorter time to achieve each success compared to the mid-air button. For each method, we divided the 32 trials into 4 blocks and used non-linear least squares to find the best fitting curve to the average success rate data. We then calculated the steepness of the first block to measure the initial learning rate. The sensorimotor regularities congruent method showed the fastest initial learning, followed by the mid-air button method, and then the incongruent method. With the congruent method, user learning peaked between trials 2 and 3. However, the other 2 methods followed an exponential curve, showing no clear inflection point, suggesting that participants may not have fully reached their learning saturation point by the end of the same number of trials. Moreover, the congruent method scored significantly higher in both overall perceived agency ratings and perceived presence ratings compared to the other 2 methods. After using the congruent method, 6 participants reported feeling a stronger sense of ownership over the time control superpower, even without being explicitly asked. This self-reported sense of ownership was not observed with the other 2 methods. Interestingly, 4 of these participants also described experiencing perceptual illusions, feeling that time had become something tangible and grabbable. To conclude, by empirically comparing 3 control methods for the time manipulation superpower in MR, we found that compared to the arbitrary mappings and the mid-air button, the control method that aligns with sensorimotor regularities led to significant performance gain, faster initial learning, an earlier achievement of near-optimal performance, and a strengthened sense of ownership towards the augmented superpower. We believe that sensorimotor regularities can offer a promising method for creating highly usable, easy-to-learn action outcome mappings that resonate with the mental models of a wide range of users. However, it is important to emphasize that the benefits of using sensorimotor regularities as design constraints were seen in just one example of superpower interaction. Future research should replicate these experiments with different superpowers. To help with this, we introduced the sensorimotor regularities constraint superpower design pathway, which can guide future work in exploring the broader use of sensorimotor regularities for action outcome mappings. For more details about this design pathway and user study findings, please check out our paper. Thank you.